All right, guys. So we have done a couple of examples on how to use this idea of dxdt or dydt, or even dzdt. Now I actually want to do a word problem. So we're going to look at number 5. So on number 5, a 10-foot ladder is leaning against a wall. If the top of the ladder slides down the wall at a rate of 2 feet per second, how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall? So we do have a couple of things going on here. The ladder is sliding down the wall, but when it slides down, of course, the bottom end of it has to push out too. So I'm going to draw a picture. Now, they've already got a picture for us, but I'm going to draw a little bit more in depth in picture because they've only got this side labeled, and I actually need all the sides labeled, at least for this example. So let me do a whiteboard here. So number 5, we had this piece was 10. Now, because we have the ladder actually sliding down the wall, and we have the ladder pushing out away from the wall, I'm going to label those as, I'm going to use X and Y. I use Y for the vertical distance because on a graph, that's Y, and I use X for the horizontal distance. You can use whatever letter you want, but that's what I'm going with. So let's talk about what else we knew. So if I read back over the problem, I'm just going to look it up in my book here. It said if the top of the ladder slides down the wall at a rate of 2 feet per second. So that's how fast it's sliding down the wall. That to me means that dy dt, because that's the change in y, right? That's what we labeled as y, or whatever letter you choose to label it as, equals, so it's sliding down. That's going to be negative 2 feet per second, because we're going down. So that's dy dt. And then they also tell us that how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall. So they're also telling us that our x value needs to be 5 feet. So what I've done is I've taken that problem, I've labeled everything I know. So I've drawn my picture, I've labeled all of my values that were given in the problem, and now I'm going to go about solving this problem. So please be aware here, since we're trying to figure out how quickly it's moving away from the bottom of the wall, in this particular problem, I'm actually going to be after dx dt. That's what I want to know. So it's really important that, so we want to know dx dt when x equals 5 feet. So that's what I'm after. So now this is a right triangle, right? Because we had a wall. A right triangle, I need to have some type of formula for a right triangle. And since we're talking about the lengths of sides, that means to me that I'm going to be using the Pythagorean theorem. So I'm going to be using the formula x squared plus y squared equals 10 squared. So that's the formula. And of course, we can rewrite this to be x squared plus y squared equals 100. And what I want to do is I'm now going to take the derivative of both sides equal or with respect to t. Now, if you wanted to, you could move things around before you start. It doesn't really make any difference. So I'm just going to take the derivative of both sides. So I'm going to do ddt, not that, of x squared plus y squared. I'm going to do ddt of 100. So if I take the derivative here, when I take the derivative of x squared, I'm going to be 2x. But because it was with respect to time, this is going to be 2x dx dt. Same thing for y. I'm going to take the derivative of y, get 2y, but this is going to be dy dt. And then, of course, the derivative of 100 with respect to time is just 0 because it was a constant. So I've got it set up to where I've got my dx dt, dy dt, and I've got my variables. So at this point, I'm going to solve this thing for dx dt. So if I solve this thing for dx dt, I can get that by subtracting 2y dy dt and then dividing by 2x. So now that I've got dx dt by itself, I'm going to plug in with what I know. So I know I've got -2. Now I don't have a y value, so this is where it's going to get a little confusing. There's no y value, so I'm going to leave my y. But I do know that dy dt is -2. And then on the bottom here, I know that I've got 2 times my x. So I'm looking for it when it's 5. Let's keep the trying to think if I want to. No, let's hold off plugging in. Let's just plug in dy dt. I'm going to do that for right now. It doesn't really matter, but I want to show you something. So here, -2 times -2 is positive 4 over 2. So this is really going to be 2y over x. So dx dt is going to be 2y over x. Now, here's the issue with that. It doesn't really help me out. I mean, I could plug 5 in, yeah. So I could change my 5 to be, or my x to be a 5. So I could do this because I know that x, I'm doing this when x is equal to 5. But again, that doesn't really help me out. So what I need to do is I need to somehow now figure out what y is equivalent to. Now, at this point, guys, this is no longer calculus. This is going to be algebra. So to figure out what y is equal to, and if I've already got x, so I'm using this x equals 5 feet, I'm going to go back to the Pythagorean theorem. So I'm going to go back here. Let me change colors. I'm going to go back here and I'm going to say, okay, well, I know that x squared is 5 squared. I don't know what y is. And that's going to equal 10 squared, which is 100. So by doing this, I can actually go through and figure out what y is supposed to be at that moment. So 5 squared is 25, plus y squared equals 100. If I subtract 25, I've got y squared equals 75. If I take the square root of both sides, the square root of 75 is going to give me y equals, that's 25 times 3. Square root of 25 is 5. So that's going to be 5 on the square root of 3. So really, that's what y is going to be equal to. So I can use that y in place here. So if I do that, I'm going to have dx dt, because I want dx dt to be a value. I want it to be a number. So I'm going to have 2 times 5 on the square root of 3 over 5. Guess what the 5's do? They are going to cancel out. So really, my final answer here is 2 on the square root of 3 feet per second. Okay, so let's talk our way back through this problem. So with this problem, I labeled everything that I knew. I went through and I set up a Pythagorean theorem. So I had x squared plus y squared equals 10 squared after I drew my picture. Took the derivative with respect to time, ended up with this statement. And because I didn't know what y was, and we should be able to figure out a numerical value for this, I went back and solved that Pythagorean theorem equation for y because I needed to know what y was when x was 5. And then that gave me enough information to plug this in. I did end up with 2 on the square root of 3. I'm glad it was positive because with the x-axis, positive means you're moving towards the right, which is exactly what this ladder is doing. So that was number 5. All right, I'm going to clear this out. Let's do another one. Guys, this is a really common problem in calculus. I'm trying to do the more famous problems that you'll see. So let's look at number 10. So number 10, a 6-foot tall person walks away from a 10-foot lamppost at a constant rate of 3 feet per second. So they're walking this way at 3 feet per second. What is the rate that the tip of the shadow, so this part here, moves away from the pole when the person is 10 feet away from the pole? Now, I see, when I look at this, I see 2 triangles. I see a big triangle that encompasses the lamppost and kind of overtakes the man here. And then I see the little triangle formed by the man. So what I'm going to do is when I write this out on the whiteboard, I'm actually going to draw both of these triangles. Now, one of the things I want you to pay close attention to, you see this 10 and x? So the distance here is going to be 10 plus x. But that's actually what I'm trying to solve for is how fast the thing's changing here. So I'm actually going to take this 10 plus x and I'm going to change that to be y. So you're going to see me go through that process here in just a second. All right, so let's oh, I don't think I did a new share here. Okay, so there's the picture that I'm looking at. So we had the 10, we've got the big triangle, we've got the little triangle. So I want to find what the rate of change is down here. So I'm going to take this 10 and x, I'm going to change that to be a y. Now let's do a new share. Okay, so on number 10, so I'm going to draw two triangles. I've got the big triangle and I'm going to have the little triangle. Man, my triangles look ugly. So I know that this bottom part was 10 plus x, right? Because we had to take the 10 that the man had already walked or was away from the lamppost with the x that he's actually going to walk. But I'm going to do something weird and I'm going to call that y because I know that I need to find the change. Now, I know that in the last problem I used x as the horizontal distance. Still using x as the horizontal distance, but I need another variable. So I could have called this a, I could have called this z, whatever. And then the little triangle, oh, we knew that was 10. And then on the little triangle, you use 6 over x. Now, the thing about similar triangles is that we can set up proportions. So I'm going to use that idea in a moment. The other piece of information that was given to us was that he's moving at a constant rate of 3 feet per second. So that was in terms of the x, right? So I'm going to let dx dt equal 3 feet per second. Okay, so now I'm going to set up a proportion. And guys, in terms of the math for this problem is actually easier than the previous problem. So if I set up my proportion, and remember you can set up your proportion a bunch of different ways, it just has to match top to bottom. I'm going to do 10 to 6 equals, so I'm going to do big to little triangle side to big triangle side. And I'm actually not going to use 10 plus x, I'm going to use y. That's why I called it y. It's much easier. And then that's going to be over x. Okay, so if I solve this proportion out, I've got 10x equals 6y. Let's set it equal to 0. So I'm going to have 10x x minus 6y equals 0. And now I'm going to go through and take the derivative of both sides. Did you have to move the 6y over? No, I just wanted to. That's because I could. So I'm going to take ddt, derivative with respect to time of both sides. And what that's going to give me is 10 dx dt minus 6 dy dt, right? Because it's with respect to time, equals, well, 0. That's one of the reasons I moved everything over. Okay, so at this point, I do know what dx dt is. Dx dt is 3, so I'm going to have 10 times 3 minus 6 dy dt equals 0. So I'm going to subtract my 30. So I get negative 6 dy dt equals negative 30. Divide both sides by negative 6. So I get dy dt equals 5 feet per second. And that's actually what I was after. I wanted to know what's the rate of this whole thing changing, not just the piece that he's walking away from the lamppost. And that's it. Dy dt is going to be equal to 5 feet per second. Again, the math behind this problem was much easier than what we did on the previous problem. Okay, guys, so I'm going to stop the video there. I'll show you a couple more examples in other videos.